The ocean functions as a unified physical system, extending across depth, latitude, and basin boundaries, without clear internal separation. Physical properties persist through shared structures that link distant regions under common constraints. Variability appears within this system without disrupting its overall coherence. The ocean constitutes a single, continuous body of water that extends across the planet's surface. This continuity is maintained despite the presence of continents, islands, and marginal seas. Water masses connect across latitudes and longitudes without permanent separation into independent systems. All major ocean regions share physical connection through open passages and deep basins. Narrow straits, broad basins, and polar seas maintain uninterrupted linkage across hemispheres. No enclosed boundary fully isolates one ocean region from another at a global scale. The global ocean covers the majority of Earth's surface area and spans all climatic zones. Polar regions, temperate zones, and equatorial areas remain part of the same water body. So, surface divisions used in naming oceans reflect geographic conventions rather than physical separation. The seafloor provides a continuous foundation beneath the water column across oceanic space. Continental margins, abyssal plains, ridges, and trenches form connected structural elements. These features do not divide the ocean into discrete physical units. Vertical continuity extends from surface waters to the deepest basins. Depth variation occurs across regions without interrupting overall spatial connection. Shallow shelves and deep basins remain part of the same global volume. Maps and classifications often segment the ocean for reference and analysis. These divisions do not correspond to physical discontinuities in the water body itself. The ocean retains spatial unity, regardless of naming systems. Global coverage includes nearly all longitudes and a full range of latitudes. Open water connections exist around continental landmasses. This arrangement supports the classification of the ocean as a single planetary system. The ocean's continuity persists over geological timescales. Land configurations change, while global water connection remains present. The planet's surface water maintains its integrated spatial form. Ocean basins are commonly identified as distinct geographic regions while remaining physically connected as parts of a single global water body. The Pacific, Atlantic, Indian, Southern, and Arctic basins share open boundaries rather than permanent separations. Each basin occupies a continuous depression in Earth's surface that links to adjacent basins through broad passages. Connections occur across equatorial regions, polar margins, and mid-latitude expanses. No basin exists as an enclosed container isolated from the others. Open water pathways surround continental landmasses and extend around the planet. Basin outlines reflect the arrangement of continents rather than divisions in the ocean itself. Marginal seas and gulfs maintain connection to larger basins through straits and open shelves. These features remain part of the same continuous system. The naming of basins provides reference for location and mapping. These labels do not indicate physical discontinuities in the water body. Boundaries between basins are conventional and adjustable across scientific and cartographic context. Seafloor structures extend across basin limits without interruption. Ridges, plains, and trenches cross from one named basin into another. Structural continuity remains consistent across basin designations. The Arctic Basin connects to lower latitude basins through northern passages. The Southern Ocean encircles Antarctica while linking surrounding basins into a unified ring. These arrangements maintain global coverage without separation. Vertical extent varies across basins while remaining part of the same volume. Shallow and deep regions occur across all basins without forming independent units. The ocean retains spatial integration across its entire basin network. Interconnected basins collectively form a single planetary system. Geographic segmentation provides organizational clarity, while physical continuity remains unchanged. The global ocean lacks internal physical barriers that divide it into separate water bodies. No solid walls, fixed membranes, or continuous obstructions exist inside the ocean to partition one region from another. Water occupies a connected space across the planet without internal enclosure. Horizontal separation does not occur across named ocean regions. Surface divisions shown on maps do not correspond to physical boundaries in the water itself. Lines used for reference remain abstract and do not alter spatial continuity. Vertical separation is also absent across the full depth range. Layers associated with depth variation do not form sealed compartments. The water column remains connected from surface regions to the deepest basins. Geographic features shape the ocean floor without isolating volumes of water. Ridges, rises, and plateaus extend across wide areas while remaining part of a shared structure. Trenches and basins mark depth differences rather than separations. Continental land masses interrupt surface coverage without creating internal division. Water continues around coastlines, through straits, and across shelves. Enclosed seas maintain connection to larger regions through open passages. The absence of internal separation applies across all latitudes. Polar waters connect with lower latitude regions without fixed barriers. Equatorial regions share the same continuous expanse. Administrative and scientific categories describe the ocean using regional terms. These categories do not correspond to material partitions in the water body. Spatial unity remains intact, regardless of classification. The ocean occupies a single uninterrupted volume. Internal division is not a defining feature of its physical structure. The global water body remains continuous across its full spatial extent. The ocean extends around the planet in a nearly continuous band of water. Surface coverage spans most longitudes without interruption. Water surrounds continental land masses and connects across hemispheres. Circumglobal coverage includes connections at low, middle, and high latitudes. Open water routes exist around southern polar regions. Northern passages link high-latitude regions across continental margins. The distribution of water forms a global network rather than isolated patches. Land interrupts surface coverage without ending continuity. Coastlines mark transitions between land and water rather than endpoints. Large oceanic regions encircle the Earth in overlapping arcs. No single continent blocks global connection across all latitudes. Water pathways remain available around the edges of landmasses. Polar regions contribute to global coverage through open connections. Southern high latitudes support uninterrupted circumpolar water. Northern high latitudes maintain connection through multiple marginal seas. Maps often depict oceans as separate areas arranged across the globe. These representations simplify geography without altering physical extent. Continuous coverage remains present despite segmented depiction. Circumglobal water coverage includes both open ocean and connected marginal regions. Enclosed seas remain linked through straits and shelf areas. Global reach persists across these configurations. The ocean occupies most of the planet's surface area. Coverage extends across nearly every climatic region. No latitude band is entirely free of oceanic connection. This global distribution supports classification of the ocean as a planet-scale feature. Water coverage remains continuous across the Earth's exterior. Circumglobal extent defines the spatial character of the ocean. Open water areas form continuous connections across the global ocean. These connections occur without fixed interruptions across broad surface regions. Water remains linked across long distances through unobstructed expanses. Large open regions connect named ocean areas into a single spatial system. Boundaries shown on maps do not correspond to closed limits in open water. Connection persists across these reference lines. Open water surrounds continents and islands on multiple sides. This arrangement allows uninterrupted linkage around land masses. No continent fully separates one open region from another at a planetary scale. Straits and wide passages maintain continuity between larger areas. These features do not function as barriers within the water body. Open water extends beyond them without forming isolated sections. Polar regions contribute to open connectivity through accessible surface areas. Southern high latitudes provide a continuous belt of open water around the planet. Northern high latitudes maintain linkage through multiple adjoining regions. Marginal seas remain connected to larger open areas through surface openings. These seas do not form independent systems. Their open connections preserve inclusion in the global water body. Open water connectivity spans nearly all longitudes. Continuous surface paths exist around the Earth's circumference. This coverage supports a unified spatial arrangement. Depth variation does not interrupt open connectivity at the surface. Shallow and deep regions coexist without dividing surface continuity. Open water remains linked across these variations. Geographic naming conventions describe open regions using separate terms. These terms do not reflect physical separation within the water. Open water connectivity remains consistent across classifications. The global ocean retains uninterrupted surface connection across its open areas. Connectivity defines its spatial character at the planetary scale. Marginal seas form integral components of the global ocean. These regions connect to larger ocean areas through straits, channels, and broad shelf openings. Their boundaries are defined by surrounding land rather than internal separation from the ocean. Each marginal sea maintains direct spatial linkage with adjacent open water. Narrow passages do not isolate these seas from the larger system. Water continuity remains intact across their connecting boundaries. Marginal seas appear along continental edges at various latitudes. Examples occur in temperate, tropical, and polar regions. Geographic placement does not alter their integration into the global water body. Surface coverage in marginal seas contributes to overall ocean extent. These regions expand the reach of ocean water into continental margins. Their inclusion increases the total connected area of the ocean. Depth ranges within marginal seas vary widely. Shallow shelves and deeper basins coexist within these regions. Variation in depth does not form closed compartments. Maps often depict marginal seas as distinct units. These depictions serve reference purposes without implying physical separation. Spatial continuity remains unchanged regardless of cartographic treatment. Marginal seas share the same water body as adjacent open regions. No fixed barriers prevent connection across their boundaries. Their waters remain part of a single global volume. The edges of marginal seas follow coastlines and island chains. These features outline shape without enclosing water completely. Open connections persist along their margins. Integration of marginal seas supports global coverage. Their spatial arrangement extends ocean presence into continental interiors. The global ocean includes these regions as connected components across its full extent. Polar regions form continuous connections with the global ocean. High-latitude waters remain physically linked to lower-latitude regions without internal separation. The ocean extends into polar areas as part of the same connected water body. The Southern Ocean surrounds Antarctica and connects adjacent ocean regions around the planet. This circumferential arrangement maintains uninterrupted linkage across longitudes. No continental barrier fully interrupts connection at southern high latitudes. Northern polar waters connect through multiple marginal seas and passages. These regions link Arctic waters with adjacent ocean areas. Physical continuity remains intact across northern boundaries. Sea coverage in polar regions contributes to global extent. Water reaches the highest latitudes available on Earth's surface. Polar coverage completes the ocean's planetary reach. Land masses near the poles shape coastlines without isolating water regions. Islands and continental edges define geometry rather than separation. Open connections remain present around these features. Maps often depict polar oceans as distinct areas. These depictions reflect geographic orientation rather than physical division. Polar waters remain part of the same continuous system. Depth variation occurs across polar regions without partitioning the water body. Shallow shelves and deeper basins coexist as connected components. Vertical extent does not create isolated compartments. Seasonal surface conditions alter appearance without changing spatial linkage. Physical connection persists regardless of surface state. The water body remains continuous across polar latitudes. Polar linkage supports classification of the ocean as a global system. High-latitude regions complete circumglobal coverage. The ocean maintains uninterrupted connection from equatorial zones to polar extremes. Surface-level continuity characterizes the global ocean across broad geographic scales. The water surface extends across longitudes with few interruptions. Continental margins interrupt coverage without ending connection. Open surface water surrounds major landmasses on multiple sides. Islands create localized boundaries without dividing the surface into isolated sections. Coastlines define edges rather than separations. Surface continuity persists across named ocean regions. Cartographic boundaries do not correspond to physical divisions at the surface. The water surface remains connected across reference lines. Coral regions contribute to surface continuity at high latitudes. Southern high latitudes support uninterrupted surface connection around Antarctica. Northern high latitudes connect through adjoining seas and openings. Marginal seas share surface linkage with adjacent open regions. Straits and wide openings maintain connection at the surface. These areas remain part of the same surface network. Surface coverage includes both wide ocean expanses and narrower passages. Narrow connections do not disrupt continuity across the planet. The surface remains linked across these variations. Surface-level connection spans nearly all latitudes. Water reaches close to both poles without forming isolated surface zones. The surface network completes global coverage. Maps often segment the ocean surface for reference. These representations simplify geography without altering physical linkage. Surface continuity remains present across mapped divisions. The ocean surface forms a connected layer across the planet. This layer supports global spatial unity. Surface-level continuity reflects the integrated extent of the ocean. Subsurface connectivity extends across the global ocean at all depth levels. Water remains physically connected below the surface across broad geographic regions. No sealed partitions exist in subsurface layers. Depth-related variation does not interrupt spatial linkage. Shallow shelves, mid-depth zones, and deep basins form parts of a continuous volume. These regions remain connected across basin boundaries. Subsurface water occupies depressions shaped by the seafloor. Basins connect through wide passages and shared structural features. No enclosed cavities isolate subsurface regions at a global scale. Ridges and rises shape the ocean floor without dividing subsurface space. These structures extend across large areas while remaining part of a connected framework. Trenches mark depth differences rather than separation. Subsurface continuity persists across latitudes. High latitude regions connect to lower latitude areas through uninterrupted subsurface space. Polar and equatorial regions share the same connected volume. Marginal seas maintain subsurface linkage with adjacent open regions. Narrow connections do not interrupt continuity at depth. Subsurface integration remains consistent across these boundaries. Maps and classifications often emphasize surface divisions. These representations do not reflect subsurface separation. The connected nature of subsurface water remains unchanged. Depth does not create isolated compartments within the ocean. Subsurface regions form a unified spatial system across the planet. Connection remains present across the full range of depths. The ocean occupies a continuous three-dimensional space. Subsurface connectivity complements surface linkage. The global water body retains spatial unity across its entire volume. The ocean covers a large portion of the planet's surface area. Estimates place total ocean coverage at approximately 361 million square kilometers. This surface area represents the majority of Earth's exterior. Ocean water extends across nearly all longitudes and a wide range of latitudes. Surface coverage includes open ocean regions, marginal seas, and connected shelf areas. These components together form a continuous surface expanse. The distribution of ocean surface area is uneven across hemispheres. Larger portions occur in the southern hemisphere, where land coverage is more limited. Northern regions contain greater land concentration, with reduced ocean surface proportion. Surface area measurements include regions that vary widely in width and shape. Broad oceanic expanses coexist with narrow passages and enclosed seas. These variations contribute to the overall total without reducing continuity. The ocean surface outlines continental margins and island chains. Coastlines define boundaries between land and water, while contributing to surface complexity. The measured area includes these irregular outlines. Cartographic representations divide ocean areas into named regions for reference. These divisions do not alter the cumulative surface measurement. Total area remains consistent regardless of naming conventions. Satellite observations and global mapping support modern surface estimates. These measurements account for the curvature of the planet. Adjustments reflect Earth's spherical geometry. The ocean surface area remains stable on short observational timescales. Minor variations occur due to long-term geological factors. The overall magnitude remains within established ranges. Total surface area defines one aspect of the ocean's physical extent. This measure provides a spatial scale for the global water body. The ocean occupies a dominant portion of Earth's outer surface. The global ocean contains a vast volume of water distributed across the planet. Scientific estimates place total ocean volume at approximately 1.3 billion cubic kilometers. This figure represents nearly all liquid surface water on Earth. Ocean volume includes water from the surface down to the deepest mapped regions. Shallow continental shelves contribute smaller proportions compared to deep basins. Large volumes are associated with extensive abyssal areas. The volume estimates account for the irregular shape of the seafloor. Basins, ridges, and trenches influence how water occupies space. These features alter local depth while contributing to total volume. The majority of ocean volume lies at depths greater than several thousand meters. Broad, deep regions contain most of the global water mass. Shallower regions occupy larger surface areas with smaller volume contribution. Measurements of ocean volume rely on global bathymetric data. Satellite gravity mapping and sonar surveys support these estimates. Refinements adjust values without changing the overall scale. Volume distribution varies across named ocean regions. Larger basins contain greater proportions of total volume. Smaller basins and marginal seas contribute limited amounts. The ocean volume remains relatively constant on short observational timescales. Long-term geological processes influence volume over extended periods. Short-term variations remain minimal in comparison to total size. Global volume estimates include all connected marine regions. Inland seas connected to the ocean contribute to the total. Isolated freshwater bodies are excluded from these calculations. Total ocean volume defines a key dimension of Earth's physical structure. This measure complements surface area and depth range. The ocean occupies a substantial three-dimensional portion of the planet. The ocean exhibits a wide range of depths across its global extent. Maximum depths occur in narrow trench regions, associated with the deepest parts of the seafloor. The deepest recorded point lies at approximately 10,984 meters below mean sea level. Depth range spans from shallow coastal shelves to extreme trench environments. Continental shelves typically extend to a few hundred meters in depth. Vast regions of the ocean occupy depths of several thousand meters. The deepest locations are limited in horizontal area compared to broader basins. Trenches form elongated features rather than expansive regions. Despite their limited area, these locations define the lower bound of ocean depth. Depth measurements rely on bathymetric surveys and acoustic mapping. Repeated measurements refine estimates without altering the established range. Variations between surveys remain small relative to total depth. Maximum depth values are associated with specific geographic locations. The Western Pacific contains several of the deepest trench systems. Other ocean regions exhibit shallower maximum values. Depth range contributes to the three-dimensional extent of the ocean. Vertical scale complements surface area and volume measures. Together, these dimensions define the ocean's physical size. The deepest points occur along tectonic boundaries, expressed as trenches. These features do not interrupt overall water continuity. Depth variation reflects seafloor shape rather than separation. Global depth range remains stable over short observational periods. Geological processes alter depth over extended timescales. Short-term measurements show consistency across modern datasets. Maximum depth establishes the lower limit of ocean extent. This measure provides a reference for the ocean's vertical scale. The ocean occupies a substantial depth range across the planet. Minimum depth across the ocean occurs along coastal margins and shallow shelf regions. These areas represent the upper boundary of ocean depth. Depth values approach zero at shorelines where ocean water meets land. Continental shelves define much of the minimum depth range. These shelves extend outward from continents with gentle slopes. Typical shelf depths remain within the first few hundred meters. Shallow regions occupy a limited proportion of total ocean volume. Despite their smaller volume contribution, these areas cover extensive surface regions near land. Their depth range contrasts with deeper offshore basins. Minimum depth varies geographically. Some coastlines feature broad, shallow shelves, while others transition rapidly to deeper water. These variations reflect seafloor shape rather than changes in ocean extent. Marginal seas include many shallow areas. Enclosed or semi-enclosed seas often exhibit lower average depths. These regions remain connected to the broader ocean system. Depth measurements in shallow regions rely on coastal surveys and nautical charting. Modern mapping refines estimates while maintaining consistent depth ranges. Shallow depth values remain well documented. The minimum depth range defines the upper limit of the ocean's vertical extent. This range complements deeper measurements without forming separate categories. Shallow and deep regions together describe continuous depth variation. Tidal flats and nearshore waters occupy the shallowest portions of the ocean. These areas fluctuate in coverage without altering minimum depth classification. The depth range remains defined by contact with land. Minimum depth contributes to the full vertical scale of the ocean. Shallow limits frame the upper boundary of the water body. The ocean extends from these shallow margins to its deepest points across a continuous depth range. Mean depth represents the average vertical dimension of the global ocean when depth values are distributed across total surface area. Scientific estimates place mean ocean depth at approximately 3,600 to 3,700 meters. This value reflects the combined influence of shallow margins and deep basins. Mean depth integrates wide variations in seafloor elevation. Broad abyssal plains contribute substantially to the average. Shallow continental shelves exert limited influence due to their smaller volume share. Different ocean regions display distinct depth distributions. Large basins contain extensive areas near the mean depth range. Smaller basins and marginal seas typically register lower average depths. Mean depth values are derived from global bathymetric datasets. These datasets combine satellite-based measurements with direct sonar mapping. Revisions refine numerical precision without altering overall magnitude. The calculated mean does not correspond to a single physical location. It represents a statistical property of the ocean as a whole. Individual depth measurements may differ significantly from the average. Depth variation around the mean spans several kilometers. Large areas fall within a range moderately above or below the average value. Extreme depths occupy limited surface area and do not dominate the calculation. Mean depth remains stable across short observational periods. Geological change influences this value only over extended timescales. Modern measurements show consistency across datasets. This measure complements total surface area and total volume. Mean depth provides a summary indicator of vertical scale. It supports characterization of the ocean as a three-dimensional physical feature. The global ocean maintains a consistent average depth across its connected extent. This value reflects the integrated form of the seafloor. Mean depth defines a central reference within the overall depth range. The ocean spans a wide horizontal extent across the surface of the planet. Water coverage reaches across nearly all longitudes and a broad range of latitudes. This span forms a continuous horizontal domain around Earth. Horizontal distance across open ocean regions measures thousands of kilometers. Large expanses exist without interruption by land. These areas contribute to the ocean's broad spatial reach. Continents interrupt horizontal coverage without ending overall extent. Water routes continue around continental margins and through intercontinental passages. No landmass fully blocks horizontal connection at a planetary scale. The ocean extends across both hemispheres with varying width. Some regions display wide, uninterrupted spans, while others narrow near continental boundaries. These variations reflect geography rather than limits of extent. Island chains alter horizontal outlines without isolating areas. Water surrounds islands, and connects across gaps between them. Horizontal continuity remains intact across these features. Polar regions contribute to horizontal span through circumferential coverage. Southern high latitudes support near continuous horizontal connection around the globe. Northern high latitudes maintain span through connected seas and passages. Cartographic projections depict horizontal extent using segmented layouts. These layouts assist navigation and mapping without altering physical span. The ocean's horizontal reach remains continuous despite representation. Marginal seas extend horizontal coverage into continental interiors. These regions add lateral complexity while remaining connected. Horizontal extent includes both open ocean and connected peripheral areas. The ocean's horizontal span defines one dimension of its overall size. This span complements vertical depth and total area. Together, these measures describe the full physical reach of the global ocean. Horizontal extent remains stable over short observational periods. Long-term geological changes modify coastlines without reducing global span. The ocean maintains a broad and continuous horizontal presence across the planet. Vertical extent classification describes the ocean according to depth intervals across its full range. These intervals organize depth variation without separating the water body into independent sections. Classification reflects measurement convenience rather than physical division. The upper portion includes surface-adjacent depths extending through shallow shelf regions. This portion covers areas near coastlines and continental margins. Depth values in this range remain relatively low compared to the global maximum. Intermediate depth ranges occupy large volumes across open ocean basins. These ranges correspond to broad areas between shallow shelves and the deepest trenches. Much of the ocean's volume falls within these mid-range depths. The deepest classification includes trench regions and narrow depressions. These areas define the lower limit of vertical extent. Their horizontal coverage remains limited relative to other depth ranges. Vertical classification applies consistently across all ocean regions. Each named basin contains a combination of shallow, intermediate, and deep ranges. No basin includes only a single depth category. Depth intervals remain connected throughout the ocean. Boundaries between ranges do not form physical barriers. Water occupies all vertical levels as part of a continuous volume. Classification schemes vary slightly across scientific references. Numerical boundaries between ranges may differ by convention. Overall, structure remains consistent across datasets. Vertical extent classification assists in describing the ocean's three-dimensional form. It complements measurements of surface area and total volume. These classifications support consistent representation of depth variation. Depth categories remain stable over short observational periods. Long-term geological processes influence depth distribution gradually. Modern measurements show continuity across classified ranges. The ocean spans from shallow margins to extreme depths without interruption. Vertical classification captures this range in an organized manner. The full extent remains unified across all depth levels. The ocean occupies a substantial proportion of the planet's surface. Scientific measurements indicate that ocean water covers approximately 70% of Earth's exterior. This proportion reflects the distribution of water and land across the globe. Surface coverage includes open ocean regions, marginal seas, and connected shelf areas. These components together form a continuous expanse across the planet. Land areas account for the remaining portion of the surface. The proportion of ocean coverage varies by hemisphere. The southern hemisphere contains a higher percentage of ocean surface than land. The northern hemisphere shows a more balanced distribution between land and water. Ocean coverage extends across nearly all longitudes. Large unreturbated stretches exists between continental landmasses. Smaller interruptions occur where continents and island chains rise above the surface. This proportional coverage influences the overall geometry of Earth's exterior. The ocean outlines continents and defines the dominant surface feature. Land masses appear as discontinuous areas within a larger water-covered framework. Measurements of planetary surface proportions rely on satellite mapping and geodetic models. These methods account for Earth's curvature and irregular shape. Refinements improve accuracy while preserving the established proportion. The proportion of ocean surface remains stable over short observational periods. Geological processes modify land and sea distribution over long timescales. Short-term variations do not significantly alter the overall ratio. Ocean coverage includes regions across all major latitude bands. Polar, temperate, and equatorial zones contribute to total surface proportion. No latitude band is entirely free of ocean presence. The share of planetary surface covered by ocean defines one aspect of Earth's physical character. This proportion complements measurements of area, volume, and depth. The ocean constitutes the dominant surface component of the planet. The ocean accounts for a defined portion of the planet's total volume. Estimates place global ocean volume at roughly 1.3 billion cubic kilometers. This amount represents a small fraction of Earth's total planetary volume. Earth's overall volume is dominated by solid material within the mantle and core. The ocean occupies only the outermost layer of the planet. Its volumetric share remains limited despite wide surface coverage. Proportion by volume differs from proportion by surface area. The ocean covers most of the exterior, while contributing a minor percentage to total planetary volume. This distinction reflects the planet's internal structure. Calculations of ocean volume rely on measured surface area and depth distribution. These measurements combine bathymetric data with global mapping models. Refinements adjust precision without altering the general proportion. The ocean's volumetric proportion remains stable over short observational periods. Changes in land elevation and basin shape occur over long geological intervals. Short-term variation remains negligible at the planetary scale. Water stored in the ocean represents the majority of liquid water on Earth. Fresh water in glaciers, lakes, and groundwater occupies a smaller combined volume. Isolated water bodies do not significantly affect total planetary proportions. The ocean's volume forms a continuous shell around the planet. This shell varies in thickness according to depth distribution. The overall volumetric contribution remains consistent across connected regions. Planetary volume comparisons exclude the atmosphere from solid Earth measurements. Ocean volume calculations remain separate from atmospheric volume. This separation maintains clarity in physical classification. The ocean's proportion of planetary volume defines its role as a surface layer feature. This measure complements surface area and depth range. Together, these values describe the ocean's scale within Earth. The Pacific Ocean Basin forms the largest continuous depression on Earth's surface. It extends across a broad expanse between Asia and Australia to the west, and the Americas to the east. The basin spans both hemispheres and crosses the equatorial region. The horizontal outline of the basin appears wide and expansive. Its shape narrows toward the north and south, while remaining broad at lower latitudes. This geometry reflects the surrounding continental arrangement rather than internal division. The Pacific Basin includes extensive open regions, as well as connected marginal seas. These marginal areas remain part of the same basin structure through open connections. Island arcs and archipelagos modify the basin outline without separating it into independent units. Depth variation across the basin is pronounced. Large abyssal plains occupy much of its interior area. Narrow trench systems occur along portions of the basin margins without altering overall continuity. The basin floor exhibits a combination of flat regions and elongated features. These elements form a connected structural surface across the basin. No enclosed sections divide the basin into isolated compartments. The Pacific Basin connects to adjacent basins through 7 high-latitude waters. Northern connections occur through passages linking to polar regions. These links maintain integration with the global ocean system. Surface extent of the basin covers a significant proportion of the planet's ocean area. Its size exceeds that of any other single ocean basin. This scale contributes to its dominant role in global ocean geometry. Cartographic representations often segment the Pacific into northern and southern regions. These divisions serve reference purposes only. The basin remains a single continuous structural unit. The Pacific Ocean Basin exemplifies basin-level organization through its size, shape, and spatial reach. Its geometry reflects global land distribution while maintaining uninterrupted continuity across its full extent. The Atlantic Ocean Basin forms a long, relatively narrow depression, extending predominantly along a north-south axis. It lies between the Americas to the west and Europe and Africa to the east. The basin spans both hemispheres and crosses the equatorial region. The horizontal outline of the basin appears elongated rather than broad. Width varies considerably along its length, with wider sections at mid-latitudes and narrower sections toward the north. This shape reflects the arrangement of adjacent continental margins. The Atlantic Basin includes extensive open regions and numerous connected marginal seas. These marginal seas maintain open connections through straits and shelf areas. Island groups and shallow platforms modify the basin perimeter without creating internal separation. Depth variation occurs across the basin floor. Broad plains occupy large interior areas. Localized deep regions appear without altering overall basin continuity. The basin connects to polar regions at both ends. Northern connections link to high-latitude seas near the Arctic. Southern connections extend towards circumpolar waters surrounding Antarctica. Surface coverage of the basin forms a continuous corridor between hemispheres. This corridor supports uninterrupted horizontal span across long distances. No internal boundaries divide the basin into discrete structural units. Cartographic representations often divide the Atlantic into northern and southern sections. These divisions assist geographic reference. The basin remains structurally unified across its full length. The Atlantic basin interfaces with adjacent basins through open southern waters. These interfaces maintain integration within the global ocean system. Spatial linkage persists across basin boundaries. The Atlantic Ocean basin demonstrates basin-level organization through its elongated geometry and continuous extent. Its form reflects continental placement while maintaining a single connected structural domain across its entire area. The Indian Ocean basin occupies a broad depression, primarily in the Eastern Hemisphere. It is bounded by Africa to the west, Asia to the north, Australia to the east, and southern high-latitude waters to the south. The basin spans tropical and temperate latitudes, while remaining open towards southern regions. The horizontal outline of the basin appears asymmetrical. Northern boundaries narrow due to continental enclosure, while southern portions widen into open oceanic space. This geometry reflects surrounding land distribution rather than internal segmentation. The basin includes extensive open regions along with several large marginal seas. These seas connect through wide openings and straits that maintain structural unity. Peninsula and island chains shape the basin margins without dividing it into separate units. Depth variation across the basin includes broad plains and localized deep areas. Interior regions contain large expanses of relatively uniform depth. Narrow trench features occur in limited areas without altering basin continuity. The Indian Ocean basin connects directly to adjacent basins through southern waters. These connections maintain integration with global ocean structure. Northern boundaries terminate against continental margins rather than enclosed limits. Surface coverage of the basin remains continuous across its full extent. No internal lines or barriers divide the basin floor. Structural coherence persists across wide geographic distances. Cartographic conventions sometimes divide the basin into regional sectors. These divisions assist geographic reference without indicating physical separation. The basin remains a single connected structural form. Island arcs along the eastern and northern margins modify basin shape. These features add complexity to the outline while preserving connectivity. Water coverage remains uninterrupted around these landforms. The Indian Ocean basin demonstrates basin-level organization through its asymmetrical shape and open southern extent. Its geometry reflects continental arrangement while maintaining continuous structure across its entire area. The Southern Ocean basin forms a continuous circumpolar depression surrounding the Antarctic continent. It extends across all longitudes at high southern latitudes. The basin connects the Atlantic, Indian, and Pacific basins into a unified southern expanse. The horizontal geometry of the basin appears ring-shaped rather than enclosed by continents. Antarctica defines the inner boundary, while open ocean defines the outer boundary. This arrangement produces an uninterrupted band of water around the southern hemisphere. The basin lacks extensive northern land barriers. Open boundaries allow direct structural connection with adjacent basins. These connections remain consistent across the full circumference of the basin. Depth variation across the Southern Ocean basin includes broad plains and localized deep areas. The basin floor remains continuous around the continent. No internal features divide the basin into separate sections. Island groups occur along portions of the basin perimeter. These islands modify the outline without interrupting structural continuity. Water coverage remains connected around these features. Surface extent of the basin spans a wide latitudinal range near Antarctica. In this black matter, water coverage has been made a secret. This extent provides circumglobal linkage at southern latitudes. The basin contributes to overall horizontal continuity of the global ocean. Cartographic representations often depict the Southern Ocean as a distinct entity. These representations reflect geographic convention rather than physical separation. The basin remains structurally integrated with surrounding ocean regions. The Seven Ocean Basin differs in form from other basins due to its circular arrangement. This form results from continental placement rather than internal segmentation. The basin maintains consistent geometry around its full perimeter. The Southern Ocean Basin exemplifies basin-level organization through its circumpolar structure and uninterrupted extent. Its geometry supports global ocean connectivity while remaining a single, continuous structural unit. The Arctic Ocean Basin forms the smallest major oceanic depression on Earth. It occupies high northern latitudes and is largely enclosed by surrounding continents. The basin lies between North America, Europe, and Asia. The horizontal outline of the basin appears compact and roughly circular. Continental landmasses define much of its perimeter. Open connections exist where the basin meets adjacent ocean regions. The basin includes broad shelf areas along continental margins. These shelves occupy a significant portion of the basin's area. Central regions remain limited in extent compared to other ocean basins. Several marginal seas connect directly to the basin. These seas maintain structural linkage through open passages. The basin remains part of the continuous global ocean despite partial enclosure by land. Depth variation across the basin includes shallow shelves and deeper interior zones. No internal barriers divide these areas into separate compartments. The basin floor remains structurally connected throughout. The Arctic Basin connects to lower latitude ocean regions through northern gateways. These connections maintain integration with the Atlantic and Pacific basins. Structural continuity persists across these openings. Surface coverage of the basin varies in width due to surrounding land. The basin's extent reflects continental geometry rather than internal segregation. Water coverage remains uninterrupted across its interior. Cartographic representations often depict the Arctic Basin as isolated. These representations simplify geography without indicating physical separation. The basin remains integrated with the global ocean structure. And so, island groups and archipelagos occur along parts of the basin boundary. These features modify the outline without enclosing the basin completely. Open water remains present between these landforms. The Arctic Ocean Basin demonstrates basin-level organization through its compact form and high latitude location. Its geometry reflects continental enclosure while maintaining continuous connection within the global ocean system. Ocean basin boundaries are defined through geographic and cartographic conventions rather than physical partitions in the water body. These boundaries provide reference for mapping and description of large ocean regions. They do not correspond to material barriers within the ocean. Boundary lines often follow continental margins, island chains, or selected meridians and parallels. These reference lines support consistent naming and regional identification. Placement varies slightly across scientific and institutional sources. Southern high-latitude boundaries are commonly drawn as continuous latitudinal circles. This approach separates circumpolar waters from lower latitude basins for descriptive clarity. The underlying water remains connected across these lines. Northern boundaries frequently follow narrow passages and marginal seas. These passages maintain open connection between adjacent basins. Boundary placement reflects geographic narrowing rather than separation. In some regions, basin limits align with prominent coastal features. Peninsulas and archipelagos guide the outline of basin perimeters. These outlines trace land geometry instead of subsurface structure. Cartographic conventions differ among mapping authorities. Some organizations recognize additional basins or adjust boundary positions. These variations do not alter the physical continuity of the ocean. Basin boundaries may shift slightly with revised geographic standards. Updates reflect improved mapping resolution and agreement. Structural organization of the ocean remains unchanged. Depth and seafloor features are not primary criteria for basin boundary placement. Boundaries focus on horizontal arrangement rather than vertical structure. This approach maintains consistency across maps. Marginal seas are sometimes included within larger basin designations. Inclusion depends on boundary criteria applied by the source. Open connections support their classification as part of adjacent basins. Basin boundary conventions support communication and reference. They organize the global ocean into recognizable regions. These conventions coexist with the ocean's continuous physical structure. Ocean basins occupy adjacent positions across the global ocean without isolated spacing. Each major basin shares boundaries with one or more neighboring basins through open geographic transitions. These adjacencies form a continuous arrangement across the planet's surface. The Pacific Basin adjoins other basins, primarily at high southern latitudes. Its broad southern margin meets circumpolar waters that connect to surrounding basins. Northern connections occur through limited gateways near polar regions. The Atlantic Basin lies between the Americas and Europe, Africa. Its eastern and western margins align closely with continental boundaries. Southern adjacency links the basin to circumpolar waters that also border other basins. The Indian Basin shares its southern margin with high-latitude waters. Western and eastern margins approach adjacent continental outlines. Open southern connections align it with neighboring basins. The Severn Basin encircles Antarctica and borders multiple basins along its outer edge. This arrangement places it adjacent to the Atlantic, Indian, and Pacific basins across continuous stretches. The adjacency remains uniform around the continent. The Arctic Basin adjoins other basins through narrow northern passages. These passages align it with lower latitude basins, despite partial enclosure by land. Adjacency persists across these openings. Basin adjacency reflects horizontal arrangement rather than internal division. No basin exists without contact with at least one other basin. Boundaries mark transition zones rather than separations. Cartographic depictions often emphasize basin borders for clarity. These depictions simplify adjacency relationships without altering spatial arrangement. Actual basin positions remain continuous. And dark space bust. Adjacency supports the organization of the ocean into connected regions. The arrangement forms a linked network across hemispheres. Basin-to-basin proximity defines the large-scale structure of the global ocean. Interbasin openings form geographic connections between adjacent ocean basins. These openings consist of broad passages, straits, and open water corridors that link large depressions of the seafloor. They maintain spatial continuity across basin boundaries. Southern high-latitude openings connect multiple basins around Antarctica. These openings extend across longitudes without interruption by continental land. The arrangement creates continuous access between neighboring basins at southern latitudes. Northern openings occur through narrower passages near polar regions. These passages link high-latitude basins to lower-latitude regions. Their geometry reflects continental spacing rather than internal separation of the ocean. Equatorial and mid-latitude openings appear where continental margins diverge. Wide gaps between land masses form direct connections between basins. These gaps remain open across large horizontal distances. Marginal seas often serve as intermediate spaces within interbasin openings. These seas connect to more than one basin through surface passages. Their position supports basin linkage without isolation. Interbasin openings vary in width and depth. Some span thousands of kilometers, while others narrow to confined passages. Variation in scale does not alter their role as connectors. Cartographic depictions frequently highlight interbasin openings as boundary transitions. These depictions assist regional identification. Physical continuity remains unchanged across mapped lines. Openings are not defined by seafloor elevation alone. They reflect horizontal arrangement of continents and island chains. Depth variation occurs without closing these connections. No basin is completely enclosed by land. Each basin maintains at least one interbasin opening. These openings ensure global integration of basin geometry. Interbasin openings contribute to the overall structural organization of the ocean. They define how basins align and connect across the planet. The global ocean retains continuous structure through these geographic links. Basin scale continuity describes the arrangement of major ocean basins as connected components of a single global structure. Each basin occupies a defined region while remaining linked to adjacent basins through open geographic transitions. The overall configuration forms an integrated network across the planet. No basin exists as an isolated depression. Open boundaries align basins into a continuous spatial system. Connections occur through wide corridors, narrow passages, and high-latitude openings. Basin outlines reflect continental placement rather than internal division. Margins follow coastlines, island chains, and shelf edges. These outlines mark shape without enclosing water into separate units. Depth variation occurs across basin interiors without interrupting continuity. Broad plains, ridges, and localized deep regions remain part of a shared structural surface. Vertical differences do not separate basins into independent volumes. Southern high latitudes provide circumglobal linkage among multiple basins. Northern regions maintain connection through limited but persistent openings. Mid-latitude connections occur where land masses diverge. Cartographic representations depict basins as distinct regions for reference. These representations simplify complex geometry without altering physical arrangement. Structural continuity remains present across all basin boundaries. Marginal seas often lie along basin edges. These seas retain open connection to adjacent basins. Their placement supports basin-scale integration. The spatial organization of basins forms a continuous pattern across hemispheres. Adjacency relationships define how basins align around the globe. No basin interrupts the overall configuration. Basin-scale continuity supports classification of the ocean as a unified physical system. Large depressions combine to form a single connected framework. The global ocean retains coherence across its entire basin structure. The arrangement of basins reflects planetary geometry. Horizontal span and vertical extent remain integrated at the basin scale. Continuity persists across all major oceanic regions. Abyssal plains are extensive, relatively level regions of the deep seafloor. They occupy large interior areas of major ocean basins. Their horizontal reach spans hundreds to thousands of kilometers in many regions. These plains display low relief compared to surrounding features. Elevation differences across wide areas remain minimal. Slopes are generally gentle over long distances. Abyssal plains occur primarily at great depths. Typical depth ranges extend several thousand meters below the ocean surface. Depth values remain broadly consistent across each plain. The surface of an abyssal plain appears uniform in large-scale mapping. Broad continuity defines their spatial character. Localized irregularities do not disrupt overall flatness. Abyssal plains often lie between continental margins and mid-ocean features. They form central portions of basin floors. Their placement contributes to basin-wide structural organization. Multiple abyssal plains exist across different ocean basins. The Pacific, Atlantic, and Indian basins each contain large examples. Distribution varies according to basin size and shape. The boundaries of abyssal plains transition gradually into other seafloor features. Ridges, rises, and trenches mark changes in elevation. These transitions maintain continuous seafloor connection. Mapping of abyssal plains relies on bathymetric data. Large-scale surveys reveal their extent and uniformity. Improved resolution refines outlines without altering general form. Abyssal plains represent one of the most widespread structural components of the seafloor. Their scale contributes significantly to the overall geometry of ocean basins. They form a foundational element of the ocean's deep structural landscape. The flatness of abyssal plains contrasts with more irregular seafloor regions. This contrast supports their identification as a distinct structural form. Their presence remains consistent across the global ocean. Mid-ocean ridges form extensive, elevated linear features across the global seafloor. They extend through multiple ocean basins as connected ridge systems. Their combined length spans tens of thousands of kilometers worldwide. These ridges rise above surrounding basin floors. Elevation differences distinguish them from adjacent abyssal plains. The crest regions occupy shallower depths relative to nearby seafloor areas. Mid-ocean ridges display a segmented yet continuous geometry. Individual ridge sections connect through offsets and curved segments. This arrangement creates a linked network across ocean basins. The ridge system follows a predominantly linear pattern. In some regions, the path curves to match basin geometry. The overall structure remains continuous across hemispheres. Ridge crests vary in width along their length. Some segments appear narrow and sharply defined, while others broaden into wider, elevated zones. These variations occur without disrupting continuity. The surface expression of mid-ocean ridges includes elongated highs and central axial features. These elements define the ridge profile across large distances. Local relief changes do not fragment the ridge system. Mid-ocean ridges intersect with other seafloor features. Transitions occur where ridges meet plains, rises, or trench systems. These junctions maintain uninterrupted structural connection. Mapping reveals that mid-ocean ridges occur in every major ocean basin. The Atlantic Basin contains a prominent central ridge. Comparable ridge structures appear in the Pacific, Indian, and Southern regions. The global ridge system represents a major component of seafloor architecture. Its scale contributes significantly to basin-level geometry. The ridges form a continuous elevated framework across the ocean floor. Mid-ocean ridges remain identifiable across varied mapping resolutions. Improved data refine ridge outlines while preserving their linear form. Their presence defines one of the primary structural patterns of the ocean floor. Oceanic trenches are narrow, elongated depressions on the seafloor. They represent the greatest depth values observed in the ocean. Trenches appear as linear features that extend for hundreds to thousands of kilometers. These structures occur primarily along the margins of ocean basins. Their placement often follows the edges of continental or island arc boundaries. Trenches form distinct outlines without enclosing isolated regions. The horizontal width of trenches remains limited compared to their length. Cross-sectional profiles show steep sides and a confined central axis. This geometry contrasts with the broader shapes of abyssal plains. Depth values within trenches exceed those of surrounding seafloor regions. Trenches define the lower extreme of the ocean's vertical range. Despite their depth, their aerial coverage remains small relative to basin floors. Trenches appear in several major ocean basins. The Pacific Basin contains multiple prominent examples. And additional trench systems occur in the Indian and Atlantic regions. The continuity of the seafloor remains intact across trench regions. Trenches connect smoothly with adjacent slopes and plains. No physical separation occurs between trench interiors and surrounding structures. Mapping of oceanic trenches relies on detailed bathymetric surveys. High-resolution data reveal their narrow form and extended length. Broader mapping confirms their alignment along basin margins. Trench outlines follow curved or segmented paths. These paths reflect basin geometry rather than uniform linearity. Adjacent trench segments maintain alignment across large distances. Oceanic trenches contribute to the overall structural diversity of the seafloor. Their extreme depth differentiates them from other features. They remain integrated components of the continuous ocean floor. The presence of trenches adds vertical range to basin geometry. Their form complements plains and ridges without altering seafloor connectivity. Oceanic trenches remain identifiable elements within the global seafloor structure. Fracture zones are long, linear features that extend across the ocean floor. They appear as continuous bands that can span thousands of kilometers. These features intersect other seafloor structures without forming enclosed regions. The horizontal alignment of fracture zones is often consistent over large distances. Many follow near parallel paths across basin interiors. Their orientation contributes to large-scale patterning of the seafloor. Fracture zones differ in elevation from surrounding areas. Some segments form subtle ridges, while others appear as shallow troughs. These elevation differences remain modest compared to major ridges or trenches. Fracture zones frequently intersect mid-ocean ridge systems. The intersections mark changes in ridge alignment without disrupting overall continuity. The ridge and fracture zone network remains connected across basin floors. The width of fracture zones varies along their length. Some sections appear narrow and sharply defined, while others broaden into diffuse bands. These variations do not interrupt their linear continuity. Fracture zones extend beyond ridge systems into adjacent abyssal plains. Their traces remain visible across otherwise uniform seafloor regions. This persistence allows them to be mapped over great distances. Multiple fracture zones occur within each major ocean basin. Dense groupings appear in some regions, while other areas show wider spacing. Distribution reflects basin geometry rather than isolated placement. Mapping of fracture zones relies on bathymetric and geophysical data. Large-scale surveys reveal their length and alignment. Improved resolution refines individual segments without altering their overall form. Fracture zones form an integral component of seafloor structure. They add linear complexity to basin interiors. Their presence contributes to the organized texture of the ocean floor. The continuity of fracture zones supports their identification as structural features rather than isolated anomalies. They integrate with ridges, plains, and other forms. Fracture zones remain consistent elements of the global seafloor framework. Seamount chains are linear groupings of isolated elevations that rise from the ocean floor. Individual seamounts appear as conical or irregular highs relative to surrounding plains. Chains consist of multiple seamounts arranged in aligned sequences. These chains extend across basin interiors and along basin margins. Their horizontal reach can span hundreds to thousands of kilometers. Alignment patterns vary according to regional seafloor layout. Seamount chains differ in spacing and height along their length. Some chains display closely spaced peaks, while others show wider separation. Height variation occurs without breaking overall continuity. The bases of seamounts remain connected to the surrounding seafloor. No enclosed boundaries isolate these structures from adjacent plains. The seafloor surface remains continuous around and between individual peaks. Seamount chains occur in all major ocean basins. Large examples appear within the Pacific Basin, Additional chains are present in the Atlantic, Indian, and southern regions. Some seamounts rise to shallow depths relative to surrounding areas. Others remain fully submerged, with significant relief. These differences do not alter their classification as structural features. Mapping reveals that seamount chains often follow consistent directional trends. These trends remain visible across large distances. The linear arrangement supports identification of chains as organized features. Seamount chains intersect other seafloor structures. Intersections occur with abyssal plains, fracture zones, and ridge systems. These intersections preserve uninterrupted seafloor connection. The surface outlines of seamount chains vary with mapping resolution. Broader surveys show general alignment, while detailed surveys reveal individual forms. Overall structure remains consistent across scales. Seamount chains contribute vertical complexity to the seafloor. Their presence contrasts with flatter regions without interrupting continuity. They represent a common structural component of the global ocean floor. Continental shelves are gently sloping extensions of continental landmasses beneath ocean water. They form broad platforms along the margins of continents. These shelves connect terrestrial surfaces with deeper ocean basins through gradual transitions. Shelf widths vary widely across different regions. Some shelves extend only a few kilometers from shore, while others reach hundreds of kilometers outward. Variation reflects continental outline rather than internal division of the seafloor. What do you think, Hugh Smith? Breathing. Depth across continental shelves remains relatively shallow compared to basin interiors. Typical depths increase gradually away from coastlines. The slope remains low across much of the shelf surface. Continental shelves occur along most continental margins. They appear around all major landmasses, with the exception of limited polar regions. Distribution follows the global arrangement of continents. Shelf surfaces appear relatively smooth at large mapping scales. Localized features occur without altering overall form. The shelf maintains broad continuity along continental edges. The outer boundary of a continental shelf transitions into steeper slopes. This transition marks a change in seafloor inclination rather than separation. Structural connection remains continuous across this boundary. Continental shelves vary in surface area contribution. Some regions contain extensive shelf coverage, while others show narrow margins. These differences influence basin geometry without fragmenting structure. Mapping of continental shelves relies on bathymetric and coastal data. Improved resolution refines shelf outlines while preserving general extent. Shelf form remains consistent across mapping scales. Continental shelves represent a key interface between land and deep ocean structure. Their broad, shallow geometry contrasts with deeper seafloor regions. They remain integrated components of the continuous ocean floor. The shelf system contributes to the horizontal complexity of basin margins. Its presence shapes the outline of ocean basins. Continental shelves form a foundational structural element of the global seafloor. Continental slopes are inclined regions that extend seaward from the outer edges of continental shelves. They mark the transition between shallow shelf areas and deeper ocean basins. The slope forms a continuous structural link along continental margins. Slope gradients are steeper than those of adjacent shelves. Inclination varies by region. with some slopes descending gradually and others more sharply. These differences reflect margin geometry rather than discrete segmentation. Continental slopes occur along most continental boundaries. They trace the outlines of continents across multiple ocean basins. Distribution follows the global arrangement of landmasses. The lateral extent of slopes can span long distances along coastlines. In some regions, slopes extend uninterrupted for hundreds of kilometers. Elsewhere, slopes are segmented by local variations in margin shape. Depth increases rapidly across continental slopes compared to shelf regions. The transition from shallow to deep water occurs across a relatively narrow horizontal distance. This change defines the slope's structural role. Slope surfaces display varied relief at mapping scales. Broad inclination dominates the overall form. Localized features do not disrupt continuity along the margin. The lower boundary of the continental slope transitions into basin floors. This boundary marks a change in gradient rather than a physical separation. Structural connection remains continuous across the transition. Continental slopes differ in width across regions. Some slopes appear narrow and confined, while others broaden across extended margins. Variation occurs without altering their classification. Mapping of continental slopes relies on bathymetric surveys. Data resolution refines slope profiles while preserving general geometry. Large-scale patterns remain consistent across datasets. Continental slopes contribute to the three-dimensional shape of ocean basins. Their inclined surfaces link continental platforms to deep seafloor regions. They form an integral structural component of the global ocean floor. The presence of continental slopes adds vertical contrast along basin margins. This contrast complements adjacent shelves and plains. Continental slopes maintain continuity within the overall seafloor framework. Continental rises are broad, gently sloping regions located seaward of continental slopes. They form transitional areas between steep slopes and flatter basin floors. The rise occupies an intermediate position along many continental margins. The surface of a continental rise appears smoother than the adjacent slope. Inclination decreases gradually away from the continental margin. This geometry produces an extended, low-gradient zone along basin edges. Continental rises vary in width across different regions. Some extend for tens of kilometers, while others reach much farther into basin interiors. Variation reflects margin shape rather than discrete boundaries. Depth across continental rises increases gradually with distance from land. Depth values remain intermediate between slope regions and abyssal plains. The change in depth occurs over a wide horizontal span. Continental rises occur along many passive continental margins. They are less prominent or absent in regions where margins descend directly into deep basins. Distribution follows global continental arrangement. The boundary between a continental slope and a continental rise is gradual. No sharp break separates these two features. Structural continuity remains intact across the transition. The outer edge of a continental rise merges with basin floors. This merging marks a shifting gradient rather than a physical division. The seafloor surface remains continuous across this area. Mapping of continental rises relies on bathymetric profiles and large-scale surveys. Improved resolution clarifies rise extent while preserving overall form. The general geometry remains stable across datasets. Continental rises contribute to the horizontal and vertical organization of basin margins. Their broad form contrasts with steeper slopes and flatter plains. This contrast supports identification as a distinct structural component. The presence of continental rises adds complexity to seafloor structure without interrupting continuity. They form connecting zones between continental margins and deep ocean basins. Continental rises remain integral elements of the global seafloor framework. Basin floor segmentation refers to the division of the ocean floor into recognizable structural regions across large basins. These regions appear as contiguous areas distinguished by shape, relief, and elevation. Segmentation describes spatial arrangement rather than physical separation. The basin floor commonly includes broad plains, elevated ridges, narrow trenches, and transitional slopes. Each region occupies a defined position relative to surrounding features. Boundaries between regions remain gradual rather than abrupt. Segmentation occurs laterally across basin interiors. Large areas of similar relief extend over wide distances. Changes in structure mark transitions between segments without interrupting continuity. Vertical variation contributes to basin floor segmentation. Differences in elevation distinguish plains from rises and depressions. These differences define segments while preserving a continuous surface. Segmentation patterns vary between ocean basins. Some basins contain extensive flat regions with limited relief. Others display more frequent alternation between elevated and depressed areas. Structural segments often align in elongated or curved patterns. These patterns reflect basin geometry and margin outlines. Alignment remains consistent across large spatial scales. Mapping of basin floor segmentation relies on bathymetric representation. Large-scale datasets reveal regional organization of structural elements. Increased resolution refines segment boundaries without altering overall patterns. Segments connect seamlessly with adjacent regions. No segment forms an enclosed or isolated unit. The basin floor remains integrated across all segmented areas. Segmentation supports descriptive organization of seafloor structure. It allows identification of repeating structural forms across basins. These forms appear in varied arrangements without altering continuity. Basin floor segmentation contributes to understanding large-scale seafloor layout. It highlights diversity of structural regions across the ocean floor. Segmentation remains a descriptive framework applied to a single continuous surface. The basin floor presents an organized yet uninterrupted arrangement. Structural segments coexist as parts of a unified system. The global ocean floor retains coherence across all segmented regions. Structural relief variation describes differences in elevation across the seafloor surface. These variations occur across all ocean basins and define the three-dimensional form of the ocean floor. This is the second floor. Relief differences appear as changes in height and depth rather than separations. Low relief regions include broad plains with minimal elevation change over large distances. High relief regions include elevated ridges, isolated peaks, and deep depressions. The contrast between these areas contributes to overall seafloor complexity. Relief variation occurs both laterally and vertically. Adjacent regions may differ significantly in elevation while remaining directly connected. These differences form continuous gradients rather than abrupt breaks. The magnitude of relief varies widely across basins. Some basins show extensive areas of uniform elevation. Others display frequent alternation between high and low regions across shorter distances. Structural relief remains continuous across basin interiors. Elevated and depressed features connect through transitional slopes. No relief feature forms an enclosed or isolated surface. Relief patterns often follow elongated or curved arrangements. These patterns align with basin geometry and margin outlines. Orientation varies without disrupting continuity. Mapping of structural relief relies on bathymetric representation. Color gradients and contour intervals depict changes in elevation. In the matrix, improved resolution increases detail while preserving large-scale variation. Relief variation influences the visual organization of the seafloor in maps and models. Distinct regions become identifiable through relative height differences. These distinctions support descriptive classification. Structural relief variation contributes to the overall spatial character of the ocean floor. It defines contrast between flat and irregular areas. This variation exists within a single, continuous surface. The seafloor presents a range of elevations across its full extent. Relief differences coexist without physical separation. The ocean floor maintains coherence across all variations in structural height. The global ocean is designated as a single physical system in scientific classification. This designation reflects its continuous spatial extent and integrated structure. All major ocean regions belong to the same overarching system. System-level naming treats the ocean as one connected entity rather than multiple independent bodies. Regional names identify locations within the system. These names do not indicate separation at the system level. The single system designation applies across surface and depth ranges. Shallow margins and deep interiors remain part of the same system. Vertical variation does not alter system unity. Cartographic and institutional references often adopt a unified ocean framework. This framework supports consistent description across disciplines. Classification remains stable across mapping standards. The ocean system encompasses all connected marine regions. Marginal seas and enclosed basins retain inclusion through open connections. No internal boundary removes any region from the system. System-level treatment emphasizes global scale. The ocean spans nearly the entire circumference of the planet. Its reach extends across hemispheres and latitude bands. Administrative conventions sometimes list multiple oceans. These conventions coexist with the single system designation. System unity remains unaffected by naming practice. The ocean system is recognized in global datasets and reference models. Measurements of area, volume, and depth apply to the system as a whole. Subdivisions serve organization without altering classification. The single system designation supports consistent aggregation of data. Observations from different regions contribute to one system record. This approach maintains coherence in representation. System-level classification distinguishes the ocean from regional water bodies. Lakes and inland seas are treated separately. The ocean remains identified as one continuous system. The global ocean retains its designation across scientific contexts. This designation reflects physical continuity and scale. The system remains unified across all included regions. The ocean functions as a planetary-scale water system, defined by its global extent and continuity. It occupies a continuous envelope across the planet. The planetary scale of the ocean reflects its size relative to Earth's surface. Surface coverage extends across most of the globe. No other liquid water body approaches this spatial reach. The system includes all connected ocean regions as a single entity. Marginal seas, open basins, and polar waters remain part of the same system. Geographic variation does not alter system inclusion. Planetary scale classification applies to the ocean's full three-dimensional form. Surface area, depth range, and total volume are treated collectively. These dimensions define the system's overall scale. The ocean system encircles continents and islands. Land masses interrupt surface coverage without fragmenting the system. Water connectivity remains present around global land distribution. This system extends from equatorial regions to polar extremes. High-latitude waters remain part of the same global arrangement. Latitudinal position does not limit system continuity. Planetary scale reference frames are used in global mapping and data sets. These frames support uniform representation of the ocean system. Measurements apply across the entire connected body of water. The ocean system is distinguished from smaller-scale water features. Inland seas and lakes are classified separately due to limited extent. The ocean retains its planetary designation through size and continuity. Global models and reference atlases treat the ocean as a single planetary feature. Data aggregation follows this system-level view. Regional detail exists inside a unified framework. The planetary scale water system represents one of Earth's dominant physical components. Its scale defines a major aspect of planetary structure. The ocean remains classified as a global, continuous system across scientific contexts. The ocean is classified as a non-biological physical system. At the system level, this classification focuses on its material properties, spatial extent, and structural continuity. Biological components are not included in this system definition. System-level description treats the ocean as a physical body of water occupying a defined portion of the planet. Its classification relies on measurable attributes such as area, volume, and depth range. These attributes remain independent of living organisms. The non-biological designation applies across all ocean regions. Open basins, marginal seas, and polar waters share the same physical classification. Geographic variation does not change system status. This system includes water as a physical substance, distributed across a connected domain. The system boundary follows the limits of connected marine water. Land surfaces and atmospheric layers are excluded from this classification. Scientific references often separate physical ocean description from biological study. This separation supports clarity in system-level categorization. The physical system remains defined without reference to life processes. Non-biological classification supports consistent treatment across datasets. Measurements and models apply uniformly across the entire ocean system. Data aggregation reflects physical continuity rather than ecological complexity. The ocean system is described using geometric and spatial terms. Horizontal span, vertical extent, and total volume define its form. These descriptors remain stable across scientific contexts. This classification aligns with broader physical system frameworks used in earth science. The ocean is treated alongside other non-living planetary components. Distinction from biological systems maintains categorical consistency. The non-biological system definition allows clear separation of structural description from ecological content. Physical attributes remain the primary focus. This approach supports neutral representation of the ocean as a material system. The ocean retains its classification as a non-biological physical system across scientific disciplines. This designation emphasizes structure and scale. The system remains defined by physical continuity and measurable extent. Structural uniformity criteria describe how the ocean is treated as a single system, despite internal variation. These criteria focus on continuity of material, space, and configuration across the global ocean. Uniformity does not require identical conditions in all locations. The ocean is composed of the same physical substance throughout its extent. Water occupies connected space across basins, shelves, and marginal regions. This material consistency supports uniform system classification. Spatial continuity forms a central criterion. All major ocean regions connect without permanent internal barriers. Connectivity persists across horizontal and vertical dimensions. Structural uniformity applies at the system level rather than at local scales. Regional differences in depth, shape, and extent do not disrupt overall classification. Variation exists inside a unified framework. The ocean maintains a continuous, three-dimensional domain. Surface, mid-depth, and deep regions remain part of the same physical body. Vertical layering does not create separate systems. Boundary definition supports uniformity criteria. The system boundary follows the outer limits of connected marine water. Internal divisions, based on geography or naming conventions, do not alter system structure. Uniformity criteria emphasize shared inclusion rather than similarity of form. Plains, ridges, slopes, and trenches all belong to the same system. Structural diversity exists without system fragmentation. Global datasets apply consistent treatment across the ocean. Measurements of area, volume, and depth reference a single system. Data integration reflects uniform system designation. Cartographic representation follows these criteria. Maps divide regions for reference while preserving system unity. Structural uniformity remains independent of visual segmentation. These criteria support classification of the ocean as one physical system. Uniformity arises from continuity and inclusion rather than homogeneity. The ocean meets system-level requirements through connected structure and shared material composition. Physical continuity markers identify features used to recognize the ocean as a single connected system. These markers rely on observable and measurable characteristics rather than regional labels. They support consistent classification across the entire ocean. One marker is uninterrupted water connection across basins and marginal regions. Open passages link all major areas without permanent internal barriers. This connection extends across surface and depth ranges. Another marker is shared system boundaries, defined by the outer limits of connected marine water. Coastlines outline the edge of the system without dividing internal regions. Islands modify boundary shape without creating separation. Continuity is also indicated by consistent, three-dimensional occupancy. Water fills a continuous spatial domain across horizontal and vertical dimensions. Depth variation does not interrupt inclusion in the system. Global extent serves as an additional marker. The ocean spans nearly all longitudes and multiple latitude bands. This broad reach supports identification at planetary scale. Material consistency functions as a continuity marker. The system is composed of the same physical substance throughout its extent. Local variation does not alter overall material identity. Mapping conventions reflect continuity markers through seamless representation. Basin outlines and regional divisions appear without closed borders. Visual segmentation does not change physical connection. Measurement practices reinforce these markers. Surface area, volume, and depth values are calculated for the entire connected body. Aggregation treats the ocean as a single unit. Polar linkages also act as continuity markers. High-latitude regions connect adjacent basins into a unified arrangement. These connections maintain global linkage. Marginal seas contribute to continuity markers through open connection. Their inclusion reflects physical access rather than enclosure. System classification remains consistent across these regions. Physical continuity markers operate collectively rather than individually. No single feature defines continuity alone. Together, these markers support recognition of the ocean as one continuous physical system. These markers remain stable across scientific references. Updates to mapping or measurement refine detail without altering continuity recognition. The ocean retains its classification through consistent physical indicators. The spatial integration framework describes how the ocean is treated as a single, connected entity across the planet. This framework relies on continuous spatial inclusion rather than regional distinction. All connected marine areas are incorporated into one integrated system. Integration is defined by uninterrupted spatial linkage. Horizontal connections extend across basins, marginal regions, and polar waters. Vertical inclusion spans from surface layers to the deepest mapped areas. The framework applies uniformly across geographic, biochemical, and sector. The principles and the deepest mapped areas. Differences in basin shape, depth, and extent do not alter integration. Each region remains part of the same spatial domain. System boundaries are defined by the outer limits of connected marine water. Coastlines and island margins outline the perimeter without dividing internal space. Enclosed land areas lie outside the integrated framework. Spatial integration treats named oceans as reference subdivisions. These subdivisions assist orientation and mapping. They do not represent separate systems within the framework. The integrated framework supports global scale measurement. Surface area, total volume, and depth ranges are aggregated across all regions. Data representation follows unified spatial inclusion. Polar regions contribute to spatial integration through circumglobal and multi-basin connections. High-latitude waters link otherwise distant regions. These links reinforce global continuity. Marginal seas are included through open geographic access. Narrow passages maintain inclusion within the integrated space. Partial enclosure does not remove these regions from the framework. The framework remains stable across mapping standards. Differences in cartographic depiction do not change integration principles. Spatial unity persists regardless of representation style. This approach aligns with system-level classification practices in earth science. The ocean is treated as a single spatial entity at planetary scale. Integration reflects continuity of space rather than similarity of form. The spatial integration framework supports consistent classification across scientific context. It provides a basis for unified description without reference to interactions or outcomes. The ocean remains defined as a continuous, integrated physical system. System boundary conventions describe how the outer limits of the ocean are identified at the system level. These conventions define where the ocean system begins and ends in physical space. On the sideline, Peter Adbaya, boundaries rely on geographic and material criteria rather than functional interaction. The primary boundary follows the interface between marine water and exposed land. Coastlines outline the system perimeter across continents and islands. This outline traces contact with land without dividing internal regions. Island chains modify boundary shape while remaining part of the perimeter definition. Water surrounding islands remains inside the system boundary. Land surfaces form exclusions rather than internal limits. Enclosed or semi-enclosed seas are included when open connection exists. Narrow passages maintain inclusion within the boundary. Complete enclosure by land marks exclusion from the ocean system. Polar regions follow the same boundary principles. Marine water adjacent to polar land remains part of the system. Ice-covered areas do not alter boundary placement when water connection persists. Vertical boundary conventions define the system from the water surface to the seafloor. The ocean system includes the full depth range of connected marine water. Subsurface layers remain inside the same boundary framework. Atmospheric layers above the water surface are excluded from the system. The boundary occurs at the water-air interface. This separation maintains clarity between physical systems. Boundary conventions remain consistent across scientific references. Mapping standards apply similar criteria despite visual differences. Boundary placement reflects shared agreement on physical limits. System boundaries are independent of naming conventions. Regional ocean names do not alter boundary extent. The same boundary applies regardless of regional classification. These conventions support consistent global representation. Measurements of area, volume, and depth depend on stable boundary definition. Data aggregation relies on agreed system limits. System boundary conventions reinforce classification of the ocean as a single physical system. Boundaries enclose all connected marine water. The ocean system remains defined by continuous physical extent and clear spatial limits. Internal structural consistency describes the way the ocean maintains coherent physical organization across its entire extent. This consistency applies despite wide variation in depth, shape, and regional geometry. The ocean remains a single connected structure at the system level. Structural components repeat across different regions. Plains, ridges, slopes, and basins appear in multiple locations. Their distribution follows global patterns rather than isolated arrangements. Consistency is evident across horizontal space. Major basins align through shared boundaries and open connections. No region displays structural isolation from the broader system. Vertical structure also reflects internal consistency. Shallow margins, intermediate depths, and deep regions form a continuous vertical range. Changes in depth do not create separate physical systems. Structural transitions occur gradually across large areas. Boundaries between shelves, slopes, rises, and basin floors remain continuous. These transitions preserve overall coherence. The same types of seafloor forms appear across different basins. Although scale and proportion vary, structural categories remain comparable. This repetition supports system-level consistency. Internal consistency does not imply uniform shape or size. Regional differences remain present across the ocean. These differences exist as variations inside a unified framework. Mapping and classification practices rely on this consistency. Structural features are identified using common criteria across regions. Representation remains stable despite geographic diversity. Internal consistency supports aggregation of physical measurements. Area, volume, and depth values combine across regions without structural conflict. The system functions using some of the original physical patterns and plants in the 17th century. The ocean maintains consistent structural logic across hemispheres. Polar, temperate, and equatorial regions share the same basic organization. Latitude does not alter internal coherence. Internal structural consistency reinforces classification of the ocean as one physical system. The diversity of form exists without fragmentation. The ocean retains organized continuity across its entire physical extent. The Global System Reference Model treats the ocean as a single, continuous physical entity for purposes of description and measurement. This model provides a unified frame that encompasses all connected marine regions. Regional distinctions are retained for orientation without altering system identity. The reference model defines the ocean through shared spatial inclusion. All connected basins, marginal seas, and polar waters are incorporated. Inclusion depends on physical connection rather than geographic naming. Global reference models apply consistent boundaries. The perimeter follows the interface between marine water and exposed land. Vertical limits extend from the water surface to the seafloor, across connected areas. This model supports aggregation of physical properties. Surface area, total volume, and depth ranges are compiled across the entire system. Measurements are reported for the unified ocean rather than for isolated regions. Cartographic products commonly adopt the global system reference. Maps depict regions within a single connected framework. Visual segmentation assists navigation while preserving system unity. Data repositories and atlases use the same reference approach. Datasets align measurements to a common system extent. This alignment supports comparability across sources. The reference model accommodates internal diversity. Variations in basin shape, depth, and relief are represented within the same system. Diversity does not modify the overarching classification. Polar connections are integral to the model. High-latitude waters link distant regions into one arrangement. These links maintain global continuity within the reference frame. The model distinguishes the ocean from non-marine water bodies. Inland lakes and isolated seas are excluded based on lack of connection. The ocean remains defined by continuous marine water. System-level references remain stable across revisions. Updates refine resolution without redefining the system. The Global System Reference Model provides a consistent basis for physical classification. This model underpins standardized reporting and mapping. It ensures coherent representation across scientific contexts. The ocean remains treated as one continuous physical system within the global reference framework. Physical properties persist across scales without clear boundaries. The system remains defined by continuity rather than endpoints, with conditions that extend beyond any fixed frame of reference.